we're going to discuss FET Phase-Shift Oscillator. A practical version of a phase-shift oscillator circuit is shown. The circuit is drawn to show clearly the amplifier and feedback network. The amplifier stage is self-biased with a capacitor bypass source resistor and a drain bias resistor RD. The FET device parameters of interest are GM and RD. We should assume as a very good approximation that the input impedance of a FET amplifier stage is infinite. The output impedance of an amplifier stage given by RL should also be small compared to impedance seen looking into the feedback network so that no attenuation due to loading occurs. In practice, these considerations are not always negligible, and the amplifier stage gain is then selected somewhat larger than the needed factor of 29 to assure oscillator action. Now, we're trying to solve one example of FET phase-shift oscillator.
It is desired to design a phase-shift oscillator using an FET having a transconductance of 5,000 microsiemens and a RD valued 40,000 ohms, and a feedback circuit value of R equals to 10 kilo ohms. Select the value of C for oscillator operation, which is the capacitor, at a 1 kHz and a RD for A is greater than 29 to ensure oscillator action. So first, we can get the value of the capacitor using the frequency in FET using the FET configuration given 1 over 2 pi square root of 6 RC. So we can get the value of RC of C. Find the capacitor for the oscillator operation. Now we are going to use the formula for the frequency of the FET configuration, which is given by F is equals to 1 over 2 pi square root of 6 RC. Now we have to derive this equation to get the capacitor. C is equals to 2 pi R F, which is the frequency, square root of 6, 1. So let's substitute the values. 1 over 2 pi, R is 10 kilo ohms, RF is 1 kilohertz, square root of 6. We can get the value of 6.5 nanofarad. Now, we solve for the RL to provide a gain of, let's say, A is equals to 40. This allows for some loading between RL and the feedback network input impedance. So, absolute value of A is equals to transconductance and the load of RL. RL is equals to absolute value of A over transconductance. Then, let's substitute the values. 50 microsiemens, 40, and this value will be giving 8 kilo ohms. Now we solve for RD. Using the equation, RL is equals to RD parallel to RD, we will get the value of RD, which will give us 10 kilo ohms. Now, on this equation, we got the value of the capacitance and the load across the RD.